All right, here's solutions problem 50 off the math subject GRE practice test. Here we're dealing with ring theory and ideals, which to be perfectly honest, I'm a little bit rusty on this stuff, but I think I can talk myself through the answer well enough. Maybe me being rusty will actually make this helpful. Maybe it'll make it go slower and force me to explain more stuff than I always do. So quick refresher on rings and ideals. A ring, kind of like a group, which you may be more familiar with, except that you have two operations. And often you denote those with plus and multiplication, but don't assume it's addition and multiplication. It's just one operation is abelian, and then you have this other operation, so it could be composition or something like that. And an ideal is a subset of that ring that satisfies two criteria. And those two criteria I listed over here. The first one is that the group that's induced by that ideal, and all I mean about that is if you take the same set but you only consider your abelian operation, so addition if you want to think about it that way, that must be a subgroup of the group that's induced by this ring. So again, ignoring the multiplication operation, just taking the addition there. That's the first criteria. The second one is that your ideal must absorb multiplication, and I wrote that in quotation marks. That's how I remember it with those words, but really more mathematically, it's saying that anytime you take an element from your ideal, you can multiply it, and on either side, doesn't matter which order you multiply it on, you multiply it on either side by any element, whether it's in the ideal or not, any element of the ring, and you're guaranteed to get something in the ideal. So element in the ideal suck up all the rest of the elements into the ideal. The easiest example, or the one that I think of when I think of ideals, is if you let your ring be the integers with addition and multiplication, and your ideal could be the even integers with, of course, those same two operations. You can see it's an ideal. I guess first it's a subgroup, because if you take any two even numbers and you add them together, then you're guaranteed to get an even number, and everything else, all the other properties of a group, you just kind of inherit. And it also absorbs multiplication, because if you take any even number and you multiply it by any number, any integer, whether that integer is even or odd, you're guaranteed to get an even number. So it sort of absorbs everything. It makes it even. That wouldn't work if your ideal were the odd numbers, for example, because an odd number times an even number is no longer an odd number. Anyways, there's a quick refresher on ideals. What you're asked in this question is to take two ideals, u and v, and they're two-sided. That just means that the products have to work from either direction, that you have to absorb things from the right or from the left. We have these two-sided ideals, and it asks which of the following must also be ideal. So I'm going to give these guys a name, or I'm going to give them names, I suppose. I'm going to call this one P for, that doesn't make any sense, maybe S for sum. Sure. So S is the set of all elements where one of the elements is from U and the other from V, and U and V are known to be ideals. And I'm asked, is that guaranteed to be an ideal? Well, it turns out that the answer is yes. Maybe I'll even write that over here. That will be an ideal. I guess we should check both of our criteria. The subgroup criteria is a little bit more straightforward, just because we have an abelian group here. By assumption, the sum of abelian groups ends up being a subgroup. So we get subgroup, I don't know, for free-ish. But the one that you'll want, or that maybe I'll show a little bit more carefully, is this second one. Make sure that we absorb multiplication. So the way I'll do that is I'll let, I don't know, little s, maybe S1, be an element from S. And I'm going to take that and I'm going to multiply it by R. R1, sure, why not? I'll call it R. And R is just some arbitrary element from my ring R. So R is from R, S is from S. And I'm only going to do S times R, but you could do R times S. You could switch the order of this to show that it really does work from either order. So I want to show that this product right here is an element of S. So how am I going to do that? Well, because S1 is an element of S, by definition, S1 must be the sum of an element from U and an element from V. So I can call them U1 and V1. So instead of writing S1, I can write U1 plus V1, because precisely because S is in this S right here, it must be able to be written as U1 plus V1. Now I can apply the distributive property and get U1 times R plus V1 times R. And the nice thing about this is U1 times R, well, I know that U is an ideal already. So U1 times R must be some element in U because U is an ideal. So maybe I'll call that U2, for example. U1 times R is some element in U, I can call it U2. Similarly, V1 times R is some element in V because V is an ideal. So I can call that V2. So I got U2 plus V2. Wait a minute, I got an element from U plus an element from V. That must be an element in S by definition. So that's equal to maybe S2, which is an element in S, and therefore I've absorbed multiplication. I took an element from S and I multiplied it by some arbitrary element in the ring, and I got some other element in S, or some element in S. So I get a yes here. I also get a yes in the third case. Why are you skipping the second one? Because I get a no in that case. I get a yes in this third case. I guess I have to again go and check that it's a subgroup. And that's relatively easy. If I'm taking the intersection of these two ideals, well, each ideal itself is a subgroup by definition. Because it's an ideal, it's a subgroup of the group induced by R, by that ring. And the intersection of two subgroups is itself a subgroup, so therefore I do satisfy this subgroup criteria. Then I also have to look at, does it absorb multiplication? Well, let's see, maybe I'll call this I here for intersection, not for ideal, although it will be an ideal. I for intersection. Let's take an element I that's in my ideal, capital I, and multiply that by an element R, which is just some arbitrary element in the ring, and you can switch the order if you felt like it. I times R is a member, is in the group U. That's not what I'm trying to show. I'm trying to show that I times R is in in I, not in U. But it is in U, and the reason it's in U is because I is in the intersection of U and V. Maybe I'll say because I is in U and U is an ideal. Right? So because I'm taking an element from an ideal, because U is an ideal, it has to absorb multiplication. So because I is in U, little I is in capital U, then little I times R must also be in capital U because capital U is an ideal. And similarly, I times R is an element of V by the same logic because, oh, this is screwed up here, because little I is in U, is what I should have written there. And that's because little I is in V, and capital V is also an ideal. So what I have is that this product is in U, and this product is in V. So I times R is in the intersection of U and V. If it's in U and it's in V, it's in the intersection, and the intersection is defined to be capital I. So what I just showed is that capital I absorbs multiplication. So I can put another check mark here, and I got another yes here. So I know 1 is true and 3 is true, so that ain't my answer. That ain't my answer. That ain't my answer. I'm down to either D or E. It'll turn out that D is the correct answer, that 2, maybe I can squeeze this in, is not necessarily an ideal, so let's give this guy a name, call him P. It's not an ideal. What I really here, I need finite sums of products, not just products. What I mean by that is if I defined P to be U1 V1 plus U2 V2 plus U3 V3 plus ... plus UN Vn, the sum of products, one element coming from U and one coming from V, then I would get an ideal, but that's not how I'm defining it here. I'm just defining it as one element from U and one element from V, and it'll turn out that does not give me an ideal. If it doesn't give me an ideal, I should be able to give you a counterexample. It's going to be a little bit messy, but I think I can do it. Counterexample. For P, which is equal to the set of all UV such that U is in U, V is in V. I got that all right. So, okay. What I am going to do is I'm going to define my ring to be polynomials with integer coefficients so any polynomial you want, polynomials with the variable or the unknown x, polynomials in x with integer coefficients, so whole number coefficients, that's my ring right there. And I guess you could check that that is a ring, although it is. And now what I'm going to define my two, whatever am I using, u and v? Yeah, let's let u, so this is an ideal 1, ideal u maybe, is the subset of this ring that is generated by 2 and x. So what I mean by this is 2 times f of x plus x times g of x, where f of x and g of x are polynomials in my ring R. So not all polynomials, only the polynomials that I can get by taking a polynomial from my ring and multiplying it by 2, and then adding to that a polynomial from my ring and multiplying it by x. If you stare at this guy for a little while, you might be able to convince yourself that this is all polynomials with an even constant term. I guess because you can generate all the rest of the terms from this guy, and then add to that the even constant term from this guy. This at least shows that that gives you containment. Anyways, that's what this is. What about my ideal v? Well, it's going to be very similar, except I'm going to generate it with a 3 and an x. So this will end up being all polynomials by the same logic, with a constant term divisible by 3. Okay, so then let's think about P. What I'm going to do is find a couple elements that are in P. So let's see, I wrote a couple down in my notes here. 3 times x plus 2. 3 is certainly in V. I don't know. I'm not even going to write that. I'll just say it. 3 is in V because it is 3 times the polynomial 1 plus x times the polynomial 0. So this guy is definitely in V. And this guy is definitely in U. I could think about that as 2 times the polynomial 1 plus x times the polynomial 1. So this is in V, this is in U. This guy, aka 3x plus 6, must be in P. Similarly, 2 times negative x minus 3, which is negative 2x minus 6, must also be in P. And that's because this guy right here is in U, and this guy right here is in V. I'll let you verify that. Okay, so I have two different elements in P. Because if I assume that P is an ideal, then it must be a subgroup. And what that means is that, specifically an additive subgroup, if I add up these two elements, I must get a polynomial that is also in P. Well, let's sum these two elements. 3x plus 6 plus, maybe I'll write this on a different line, 3x plus 6 plus negative 2x minus 6 is equal to x. And you're like, yeah, so who cares? Well, unfortunately, x is not a member of P. Wait, how could x not be a member of P? Well, try it. Try to write the polynomial x by taking an element from, where did I write it? U, and another element from V, and you won't be able to do it. Maybe that's enough for me to just, oh yeah, you're right, you can't do that. But in case you're having trouble seeing that, think about it like this. This is a polynomial of degree 1. If I'm going to create a polynomial of degree 1 as a product of two polynomials, well then one of those polynomials must have degree 1, and one of those polynomials must have degree 0. A degree 0 polynomial is a polynomial just equal to a constant term, not 0. So f of x equals 2, f of x equals 3, f of x equals 4, that kind of stuff. If that constant polynomial came from U, its constant term must be even. If that constant polynomial came from V, its constant term must be divisible by 3. So either way, when I take two polynomials and multiply them together, one of those two polynomials is a constant term, and that constant term is not the number 1. But there's a problem. The only way you can multiply together two polynomials in this ring and have x be the answer is if those two polynomials are 1 and x. That's the only possible way you can multiply together two polynomials from this ring and get this as the product. But this 1 is not an element in U, and 1 is not an element in V. So what's going on is that I have two polynomials in P, but their sum is not in P. So what that's saying is P does not give me an additive subgroup. So therefore, so P is not an ideal. There must be an easier counterexample out there. I don't know. Maybe there is. I spent 10-15 minutes researching it, and I couldn't figure out one. I found this was off Stack Exchange or somewhere I read this, and just kind of reworded it into my own words and used that for your counterexample here. So this is this must be an ideal, this must be an ideal, but 2 does not necessarily have to be an ideal. So therefore my answer is D.